Okay, so that's us up and recording there. So, this recording, what I'm going to cover is a thing called SIFT, which is Scale Invariant Feature Transform, and it was originally it's a paper by a guy called David Lowe. Now, it's a very important. It was a very important kind of landmark within computer vision. It's considered one of the most important things in the last 2 decades. It wasn't really until deep learning came along that we really seen another big jump in terms of computer vision. So SIFT, along with another thing called HOG, which is histogram of oriented gradients, which you've probably came across as well, because Triggs, who's one of the people in the assignment that I gave you, was also involved in writing that paper. I don't go through HOG here, but there's plenty more of these that I could go through. I've picked one of them in particular to go through because this is kind of the one that's sparked them all off. But there are others called SURF, and there's one called root SIFT, and then there's loads of other variants from there that you can look at. Histogram of oriented gradients is a little bit more looking at the entire image, so it's generally looking at much larger areas. But once again, you can tweak the numbers in it in order to do something a little bit more like SIFT, and it used a lot of similar ideas. So this is very much an idea that was of its time. So the one thing about this is that it is patented by the University of British Columbia, and that's why you've seen so many other people try and come up with other variants that were very similar or did something very similar, but that were outside of the patentability of this. So if you use this in a commercial context, you do actually have to pay a royalty to the University of British Columbia. Any of you that work in companies, I'm curious to, have you ever come across, do people use this in industry, or do they try and find some way around it? You may not know the answer to that if it's not an area that you're in. I'm curious, does anybody actually pay for it? Just while Olivia's typing there, by the way, it's also believed to be similar to systems that evolved in primate visual systems, was the idea. Oh yeah, so I can see how that'd be useful. So in other words, that if it turned out that it was better, you'd have to consider doing it. Yes, so it will be quite expensive in terms, I assume you mean in terms of computation there, as opposed to just cost. Yeah, and that certainly is the case. So when it was released, it was close to real time. Now, of course, we've moved on with Moore's law, but embedded systems are always still very restricted. So it is quite expensive, and you're going to see quite a lot of that in it. But then there's all sorts of other mechanisms where they try and maybe take some of that complexity out in order to do something else. Okay, but this is one of the things about the paper SIFT, and I would advise you to read it, is that it's a very well written paper and it's very thorough. So it is good to see just, particularly in a lot of situations, we see these places where somebody comes up with a particular number and they say use a number like 0.05 or something like that as a particular constant in things. And it's maybe not well explained why they decided to pick that number. David Lowe does a very good, thorough examination of every number that he picks, and even for just that reason, it's good to read. However, it is 26 pages long, so there's quite a bit in it. So the goals of SIFT, firstly, they want to extract distinctive invariant features, i.e. it should be possible to correctly match a feature in one image against a database of many images. So rather than just going and searching in each other image, we should be able to have some form of a descriptor so that we can very quickly just go through a database in other images, find that one, and then go to that position in that image and pick it out. Okay? And we want to be invariant to as many things as possible in terms of the sort of things that could happen within an image. In other words, our scale could change, the lighting could change, it could rotate, and it could also deform in terms of our projective transforms as well. So feature descriptors should be invariant to scale and rotation, firstly, and they should be robust. Now, robust is different from invariant. Invariant means that it's not bothered by it at all. Robust just means that it's pretty good, but it can sometimes fail. So it's robust to affine distortion. So the sort of things that you're going to see in terms of it's going to change more than scale and rotation. Okay, so your angles and so on could change. Changes in 3D viewpoint. So again, your projective. Addition of extra noise in an image, and a change in illumination. So you need to be robust to those, and that's what SIFT set out to do, as well as being invariant to scale and rotation as well. So if you think back to something like optic flow, which was a very simple system, it required brightness constancy. So it needed the brightness to stay constant, and it needed small changes in viewpoint. If you had a large change in viewpoint, you ran into trouble. SIFT's goal was to overcome all these issues. So in particular, it's useful for the wide baseline case. So where optic flow was only useful in the small baseline case, SIFT's goal was to try and be used in a wide baseline case where there could be quite a distance between, in terms of pixel position in an image, between where a descriptor was in, or where a feature was in one place and where it was in another image. Okay, so very useful for that. So the advantages of SIFT, the features are local, first of all. So they are robust to occlusion and clutter. So what we mean by a local feature, if you take, for example, when we go back right back to our original lecture, and I showed you some histograms there, those histograms tell you something about the entire image, but they don't tell you about something specific, where within the image something was. So they're quite an interesting descriptor of the image in one way, but they're a global descriptor. These SIFT features are local features, so they tell you something about local parts of the image, and that means that if you then have occlusion and clutter, in other words, things getting in the way, we can still usually tell from that it hasn't changed. Whereas if you have clutter and occlusion for something like a standard histogram, then that's going to change the image quite considerably. Okay. So they're local. Individual features can be matched to large databases of objects. Many features can be generated for even small objects. So typically, something like a 500 by 500 pixel image will produce approximately 2,000 stable features. So that's a lot of features that it can do. It's not quite dense features because you might find that they're all in particular small areas and so on. But it does get you a lot that you can go looking for. At the time SIFT was introduced, it had near real-time performance. In the decade and a half that has passed since, computer hardware has increased in relation to Moore's law, so you can assume that it can certainly be done in real time now, but that all depends on your hardware. So if you're using an embedded system, where is a current embedded system that might be on an automobile compared to a fast computer back in 2003, 2004 when this was being tested? And the realities are that our embedded systems now, while they've taken on all those new hardware changes, they're all the time trying to slow down their processor in order to use less energy, and that means that computational budget is something that we're going to have to care about forevermore, because we're always going to want to run things slower and try and do fewer computations. So whether it can run in real time is a matter for power and resources of the hardware platform. So here are the major stages, and I want you to kind of internalize these as being the major points along the way of what we do in SIFT. There's only 4 of them here, but then we're going to look at each one of them in detail as to what we do. So the first thing we do is we have a scale space extrema detection. So this, oh dear, didn't spot that earlier. So this first stage of computation searches over all scales and image locations. Now, how do we can obviously look at all different locations within the image, but how do we do different scales? Well, we just covered that in the previous class. We do it by using a pyramid. So it's implemented efficiently by using a difference of Gaussian function, a difference of Gaussian pyramid, to identify potential interest points that are invariant to scale and orientation. So where two features that show up in 2 images, they might appear in different locations within the image, but they also might appear at a different scale, and so our pyramid should be able to show them up as particular extrema at different points. So that's the first thing. We need to create our pyramid, and we need to go looking for some of these extreme points. The extreme points being the most significant points that we can find within it. After that, we do a thing called key point localization. So at each candidate location, a detailed model is fit to determine the location and scale. Key points are selected based on measures of their stability. So the thing is that when we do the scales, and we do our where we look within the image, that's somewhat coarse grained. And while we might find an extreme point somewhere, it might actually be that is somewhere between the actual key point is somewhere between it and one of the other samples, either in terms of scale or in terms of spatial, in terms of the spatial arena. So from that point of view, what we do is we actually do some fitting to try and figure out, well, is the scale point here or is it somewhere close by? So that's the second part, because we want to have we want to be pretty sure about where the feature is within the image and at what scale it's at, so that we can then find it easily when it goes to another image. The third point that we do is orientation and assignment. So one or more orientations is assigned for each key point location on a local image gradient. So the idea here is that within the image, wherever we've located that our key point is and whatever scale it's at, we look at all the gradients around within a certain distance, and we'll talk about that later as to exactly what sort of distances we're going to look at. And we basically do a totting up of the different gradients, what directions that they're in. We can do that with a histogram basically, and we can then find, well, okay, what's the dominant direction? That dominant direction then becomes integral to the actual feature that we have. So our feature will now have where was it located, what scale was it located at, and what is its orientation. And then everything that describes it from then on is all relative to those three items. Okay, so all future operations performed on image data that has been transformed relative to the assigned orientation, scale, and location at each feature, thereby providing invariance to these transformations. So as I mentioned, this is both a feature detector and a feature descriptor. So where something like Harris, the Harris corners and so on, that was quite good at detecting some important points, but it didn't have much of a descriptor, and that meant that you couldn't vary too far from your original point. You could only vary over a small baseline, or otherwise, if you jumped to the other end of the image, there was no guarantee that the two eigenvalues that you had, or whatever that information that you had, that was going to uniquely tell you a point that was somewhere a long way away in the image. Generally didn't work over a large scale or a large baseline. Whereas these, we want to then have a robust descriptor that says, okay, if we find the exact same descriptor at a different location, at a different scale, at a different orientation, but the descriptor looks the same, then we've probably found the same point. Okay, and that's the idea, and that's what makes it very useful for being able to search through many images and maybe thousands of descriptors in different images and go, hang on, I found one that's the exact same here in terms of its description. It just happens to be at a different scale, a different orientation, and a different position. So the key point description then is a big point that gets added on here, and to some extent you could take points 1 and 2 and plug in Harris there at that point if you wanted to. Okay, so the points 1 and 2 where you find your localization, admittedly the whole scale space and the key point localization that David Lowe suggests is probably much better than Harris. You could go and replace it with some other version. So they're two kind of separate sections. One is finding them, the other is making sure that we then are able to have a descriptor around them. So the key point description, the local image gradients are measured at the selected scale in the region around the key point. So this is important because when we measure the gradients, we measure a certain number of them around the key point, but we need to measure it relative to the scale that we're at, so that if we find it somewhere else at some other scale, we measure relative to that so that the two things will show up the same. So these are transformed into a representation that allows for significant levels of local shape distortion and changes in illumination, and still the histogram or the descriptor should look quite similar. Okay, so that's the idea. That's the 4 main stages, and then we're now going to go through them in detail. So the problem with many feature detectors is that they are good if the feature is of just the right size. Okay, but if it's too big or too small, then they don't detect it. This is also an issue if the scale in the image changes as a feature may be found in one image but not in another. So it can't be matched then if that's the case. So if we change the scale from one image to another, and we were able to find with our particular feature detector was very good at finding features at a particular scale, it won't find it in the other image even though it's there because it's at a different scale. So if you think about the candy edge detector or the Laplacian of Gaussians, the scale is determined by the sigma value, okay, which is the size of the kind of blob or circle that we're looking for. So you'll sometimes hear these things called blob detectors as well, because they're looking for particular sizes of blobs. So if we want to look at multiple scales, we can apply the detector at each of these sigma values, but how then do we combine the results? So we can do that. We can literally look through the image at loads of these different sigma scales, but it's a matter of then how do we combine all of these together and try and say where they are in terms of a scale. So there's a lot of earlier work was done on this, so it wasn't like David Lowe was working in a vacuum here. He built on a lot of what came before. So Ellen Hildreth, who was we mentioned in some of the early lectures, worked with David Meyer. I can't remember his first name. I think it's David Meyer. Was used a spatial coincidence assumption, which was basically the idea that if the zero crossings coincided over several scales, then they are physically significant. So what the idea was there, that she was looking for zero crossings or kind of edges, and she was off the impression, which was correct at the time, that if those appeared at different scales, that it must be a significant edge because it was appearing at different scales. And Andrew Witkin, in his paper Scale Space Filtering, did something similar, and he applied a whole spectrum of scales, and then he plotted the zero crossings versus the scales in what he called a scale space. This was one-dimensional as it happened, and he determined stable features as ones that were stable over a range of scales. He did it in a slightly different way, but it's the same idea in terms of stability. Scale is about the size of the sigma value we use in the Laplacian of Gaussian function. Of course, because we do difference of Gaussians, we're effectively doing the same as the Laplacian of Gaussian. Different size sigma will give different local maxima at different positions and scales. So unlike where the Laplacian of Gaussian was used before to find zero crossings, we're actually looking for maxima and minima here to try and find, to detect different things. Unlike Witkin, we're going to use the one best scale here rather than trying to find things over several scales, i.e. the one with the highest maxima. Now I should say highest, I should really say, instead of maxima, we should say extrema, because it could be a minima as well because of the negative and positive values. So wherever you see maxima there, we're talking about maxima in terms of its absolute value as opposed to maxima in terms of just normal value. So building a scale space, all scales must be examined to identify the scale invariant features. An efficient way to compute the Laplacian pyramid is by a difference of Gaussians. So this was outlined in the previous lecture, and we have this diagram here again, which I've written a few notes on just to maybe show it to you. So this is from David Lowe's SIFT paper. And what he's showing here is that we add a particular resolution of image. What we do is we smooth it with a particular sigma value here, and then we smooth it with k times that, and we do a subtraction, and this gives us a difference of Gaussian. And we're looking for extrema within this, so extreme values, either negative or positive. What we then do is we take a further smoothing of the image, and we subtract that from this one, and that gives us another one of these. Okay, so these difference of Gaussians here, we want these to cover an entire scale, and what we then do is we then subsample the image. So each point in each kind of layer in this pyramid will have several scales within it, okay, which we call an octave. What we then do is we resize the image down for these ones. And what we find is that, let's say, for example, in this particular case, that k is a value of the square root of 2. Okay, so if we have sigma here, if we have k times sigma, that's obviously the square root of 2 by sigma. And if we have k squared, the k squared is going to be, so k squared is going to be equal to 2. So that means that the size of the smoothing on this one is twice the size of the smoothing on this one. And that's effectively the same as smoothing a smaller image with the smaller value of sigma. So what we generally do when we resize the image in order to go to the next one is we actually take one of the ones from out here, and we start at that value again, and we start moving up. Okay, now this can cause quite a bit of confusion because it can look fairly obvious, then you think about it a bit more and it's one of those things that you go, no I haven't got it, yes I have, no I haven't got it, and so on. So again, what David Lowe did was that he did quite a lot of testing in terms of these in order to decide how many of these he should do. In other words, how many scales should we look at within each octave? And he actually determined more than what's here. He determined that we should have 3 scales. And actually, I've made a mistake on the next slide because I originally looked at this and said, well, there's 4 there, and he was doing 3. But in actual fact, he needs a 5th image in order to do. He needs a 5th one of these up here in order to do 3, and I'll show why that is in a moment. Okay, so this is the idea. Now, just to be aware, testing this image here and this one here will actually find you similar sort of things, and that's because this one is using k to the power of 4. This is only using k squared, but this is only half the size. And so it effectively comes up the same. So this term octave is a little bit confusing here as well, because octave normally means something to do with the number 8. And it refers to, in terms of audio, when we have a doubling of frequency, musicians normally split that up into 8 segments, which is the typical scale. So you're probably all familiar with the do, re, mi, fa, sol, la, ti, do, okay, which I'm not going to sing. I've said them all at the 1 frequency, as you noticed there. I spoke it. But that idea there, that what happens is there's 8 of those, first of all, and that's where the octave idea comes from. So that's what they mean by this. But in effect, what they're talking about is a halving of frequency or a doubling of frequency. And in just the same way that with those, when you go from, you go do, re, mi, fa, sol, la, ti, do, that do is the first do of the next octave. Okay, so they share that. If we want to look at a single scale on its own, we need to include both of the do's on each side, and that's what we have here. So generally speaking, when we're looking on these, we only look on one particular octave at a time, and that's why even though these two will have very similar information to them, it's not easy for us to compare this over to this because they're not the same size. So that's why we need those. Now, what Lowe determined, and as I say, if you go through his paper, he's very rigorous about talking about the sort of numbers that he comes up with. So for starters, he talks about starting with a sigma value of 1.6, and so that's his starting value up here for that. But the other thing that he does is he decides, he does quite a lot of experimentation to decide how many scales he should have. And he decides to have a number of scales of 3. And this is where a lot of the confusion comes in, because of course if you look at that, if you look at this, there looks to be 4 of them. But in actual fact, he's referring to the ones in here, because when we do a comparison, we need to compare, I'll use maybe a smaller one there, we need to compare that with the ones here, the ones around it, and the ones above it. And in this one then we need to compare that with the ones above it there and the ones below it here. But in the top one here we've nothing to compare with, and in the bottom one we have nothing to compare with. So in actual fact what he wants is, he wants 3 of these in here, another one in there, so that there will actually be 5 from top to bottom there, and there will be 6 of these in order to actually compute that. Because he states in his paper, and you'll see it, where he says S plus 3 is what is required. Now the other thing is, so if he wants 3 scales, for example, he's going to need 6 of these original images, so we only have 5 of them there, as you can see. One other important point is that because even though this is the diagram he used, but he then says that 3 turned out to be the best one, what that also means is that you've got to change your k value. Your k value should be 2 times 2 to the power of 1 over s, which of course in our case here was 2 to the power of 1 over 2, which is of course the square root of 2, which is what we had down here. But because he's putting in a third one of those there, he's going to have 2, or the third root of 2 is what he's going to have to use as his change of sigma as he goes. Okay, so I just want to go through that in a bit of detail, because if you read the paper, that's quite confusing. At the end of the day, most people just use this as, you know, somebody has already implemented it, and as well as that, he found that was the best result, but that's not to stop you going and using different values if you find that there's some reason to use more scales than that in your search. Okay, so I even have the mistake here because I actually said smaller than shown on the previous diagram. It's actually larger than shown on the previous diagram. So Lowe determined that the best number of scales per octave was 3. The SIFT paper is, as I say, a masterclass in how to find the best parameter values, and it's worth reading it just for that, to get the idea of the rigor that he goes through in order to determine the best values for what he was choosing. So this is where I talk about the peak detection. So what happens is that in each one of our scales, what we do is we take to detect the peak in the scale space. We want to know the extreme values. So we take a pixel X here. Okay, so that one there. We do with that there. And what we do is we compare it to the 26 pixels in the current and adjacent scales, which are shown in green. So the 8 pixels of its neighbors around it, and we also test it with the 9 above it and the 9 below it. And that's why I said that if we were to test this one and there's nothing above it, that's no good to us. We can't do an actual test. So this is why he wanted at least 3 that had this circumstance where there was 1 below it and one above it, so that he could actually test over a full octave. Three scales over a full octave. So it's the point is selected if it is larger than all of its 26 neighbors or smaller than all of its 26 neighbors. So if it's in either of those circumstances, so this is why we talk about them as extrema rather than a maxima, because the maxima can give you the impression that it's only the top one. So that's why I've called it extrema here. So what he's looking for is any extreme within those, and if it's extreme enough to be different from all of its 26 neighbors, then we keep it. Okay. Now you'll find then that if you go up to any of these other pixels here, let's say that one there, that can't be bigger than all of its 26 neighbors or smaller than all of them, because this is one of its neighbors here. So you can see that we're going to eliminate an awful lot of our pixels relatively quickly by going through this process. That said, we still want to refine the results because we don't want to keep all of these. So we need to remove the extrema that are poor candidates. So the thing is that if you're in a section of the image where there's nothing much going on, let's say it's just very clear sky or something like that, and there's not much, there's no real features there, the chances are there will still be, due to noise or something like that, there will have to be an extreme value somewhere. Okay, so one of them will have to be chosen as bigger than all of the other ones or smaller than all the other ones, or even if it's it might only take a small difference for that to happen, but it still wouldn't be a useful feature to keep. So first, the candidates are tested against nearby data for location, scale and rotation, or ratio of principal curvatures. So ratio of principal curvatures is something we'll come back to in a minute, but it's very similar to what we saw with the Harris detector. So firstly, if the points have low contrast or are poorly localized along an edge, they are rejected. So to do this, they use a Taylor expansion, which you've seen before. We saw this back when we looked at Harris, where we did a Taylor expansion and we just used the linear approximation. So we only used the first 2 parts of the Taylor expansion. Here we're using the first 3 parts of the Taylor expansion, which uses up to quadratic terms, and it also means that you're using second derivatives here. Okay. So rather than this being a linear approximation, this is approximating to a quadratic, which is this sort of thing here or this sort of thing here. Okay, so we're comparing it to that sort of thing within our image. So and there's formulas given for it there. So the extremum x hat is determined by taking the derivative of this function with respect to x and setting it to 0. So in other words, finding where's the 0 point of our quadratic function here. So that's the derivative of this function up above with respect to x. So if the offset x hat is more than 0.5 in any dimension, it means that the extreme is closer to a different sample point. And this is done over the 3 different points. So it has to be done in x, y, and the scale. So what they're basically saying is there that, let's say you sample some point and you think that this is an extreme value, but when you go and fit this quadratic to it, rather than it turning out that it comes like that, which perfectly fits it, instead what they find is that, let's say for example that it hits it there, okay, And what that would then tell you is that actually your extreme point is actually somewhere slightly off where your current sample is. Now, if that is more than 0.5 in any direction, so in other words in x and y or in sigma in terms of its scale, then it means that the extremum is actually closer to a different sample point. In which case it's moved and the interpolation reperformed. So the final offset x hat is added to its sample point to get the interpolated estimate of the location of the extremum. Okay, so that we know exactly where that is. The function value at the extremum, dx hat, is used for rejecting unstable extremum with low contrast, and it's given by this formula here. And so basically what Lowe suggested was that if the value for this function here was smaller than 0.03, then you would discard it. That would suggest basically that it was low contrast. Now, low contrast basically means that you're looking at some maybe section of the sky or something like that, or maybe some section of a plane wall which has very little information in it. So we're not talking about the same as an edge, which we're going to deal with in a minute, which is hard to localize along. This is where we just have low contrast in every direction. We still found an extremum, but it's an extreme of something very, very, very small. Just to make the point that in terms of 0.03, this refers to pixel values being between 0 and 1 rather than between 0 and 255. So oftentimes for these mathematical operations, what we'll do is we'll normalize the image so that its maximum value is 1 and its minimum value is 0, and we operate within that range. So this 0.03 might seem a very small value, but that's assuming that full brightness is a value of 1. Okay, so that just to be clear on that. So that clears out any features that turned up with an extreme point, but they were an extreme where there wasn't much happening, which we can kind of think of as a big fish in a small pond, and so therefore they're removed if they're below a certain value. And of course we do have freedom maybe to change that value, but this is the one that Lowe suggested over his experiments. So we have the extreme removal in the different ones here, right? So in the first case, this is where we have all of the different possible values, all the different extremum. Then this is what happens when we remove the ones that are of low contrast, and you can see that a number of them have been removed. And if you look at the paper, you'll see the exact numbers that he dealt with in this particular example. So he removes a few hundred by doing that, and then this one is removed. The ones he removes are the ones that are along edges that are not easy to localize. So if you remember before when we said that if we had an edge there and we then came along and we found a feature that was on that, like that, or maybe draw it in a different color. So we find a feature that's on that, that's something like that. The problem is we can't tell if we go and move that somewhere up here, it looks the exact same because it's still only got one in one direction. Whereas if we took the example whereby, and you saw this with Harris as well, just change that to black. If we had something like a corner here, and you then come along and you find something on it there, we've got gradients going in two different directions there, and so therefore if we go and move this guy down here, that's going to look different, and if we move it over here, that's going to look different. But if it shows up somewhere else with the exact same thing, then it shows up as a reasonable point. So the idea here is that we want to get rid of those edges. Now, if you remember the features that show up as an extreme point but are only in one direction. If you remember how Harris dealt with this, he had that structure matrix, and he looked at the eigenvalues of the structure matrix and decided that if one of them was very small, you saw all the different ways, I won't go reiterate them, you did a full assignment on it, but there were all the different ways of looking at the different eigenvalues to determine what made a good one and what didn't, because of course I'm showing ideal cases here, but they were non-ideal. So we deal with them slightly differently here, in that we use a thing called the Hessian Matrix, which I also mentioned to you as part of your assignment. So a poorly defined peak in the difference of Gaussian will have a large principal curvature across the edge, but a small one in the perpendicular direction. So principal curvature can be computed from a 2x2 Hessian matrix H, computed at the position and scale of the key point. So this is where we, in both the x direction and the y direction, we get the second derivatives now rather than the first. If you remember from the M matrix, or sometimes called the A matrix that we used in Harrison-Stevens, what we did was we just squared those first derivatives. Here we're getting the actual second derivatives of them here. The eigenvalues of H are proportional to the principal curvatures. So more curvature means that you've more of a bowl there going on. So in the same way as the structure matrix M in Harrison-Stevens, we can determine something about the two eigenvalues without actually calculating them. So we can use the trace or the determinant of the Hessian matrix, and that can then generally be done relatively quickly. Okay. So the important test here is whether the eigenvalues are different from each other in size. If the ratio is above some threshold or, then they should be eliminated, and low uses the value of or equal to 10, which means that one of the eigenvalues is 10 times the size of the other. That suggests that we've got an edge going in that direction. Now, of course, Harris and those were very concerned about the overall size of the eigenvalues as well. We've dealt with that back at the contrast thing, so it's not of such concern here. As I say, this is relatively fast to compute, but relatively Hessians themselves can be slow enough to compute, and particularly if you have to go getting inverses of them and so on. But it's reasonably fast, and that's what they used in this particular case. See, Vin has a question there, so just want to hang on. It's probably on this. So is this comparing the scales of the image or the feature? So this is comparing well, okay. So we're dealing with a feature in a particular location, but we're looking at it across. We're looking at it in terms of its spatial, but also in terms of its scale. So what I kind of didn't mention it in detail, but we're not just dealing with a two-dimensional quadratic here. We're dealing with a three-dimensional here, because we're also dealing in terms of sigma. So the idea here is that we're showing x and y in that particular direction for looking at that. But in some of the other information, what we're actually looking at as well is we're looking at in terms of so when we're trying to find the appropriate when we're trying to fit it to the appropriate maxima, we're dealing also in terms of scale at that point. Okay, so it's a little bit confusing there for the different things, but in terms of finding the exact position, we want to find in terms of x and y and in terms of scale. But then in terms of contrast and in terms of whether it's along an edge, we're really only concerned about the x and the y at that point. Okay, but we're concerned about the x and the y at that particular scale. So what we're using at that point, once we've decided our definite scale, we're going to one of these images here to go and find it, rather than trying to go back to the original image. Okay, so hopefully that makes a little bit of sense. But you can see how it gets quite complex. This is quite a complex algorithm. So we need to achieve rotation invariance now of the key points, and this means assigning a consistent orientation to each. So the scale of the key point is used to select the Gaussian smoothed image L with the closest scale, so that all the computations are performed in a scale invariant manner. So going back to this, rather than looking at the so this in here we were looking for extrema. Now what we're going to do, when we know the scale, we're going to pick one of these smoothed images. So we're going to go back to one of the original images to go about finding the to go about dealing with the orientation. So the scale of the key point is used to select the Gaussian smoothed image L with the closest scale, so that all computations are performed in a scale invariant manner. So we don't want to be looking at the wrong distances from our current pixel for determining our gradients by picking the wrong scale, effectively. So that's why it's important that we pick the scale that's associated with our feature. So for each image L, X, Y at this scale, the gradient magnitude M, X, Y and the orientation theta xy is pre-computed using pixel differences. Now we say pre-computed here because we're going to use these again later. So what we're going to do is we're going to compute them all at this point and then reuse them. So what that means is that x and y, and bear in mind that x and y depends on our sigma value here, okay, because it depends on which version of L that we're dealing with, so which image that we're dealing with. So the way we do that is basically we can do our orientation by basically just you can see it's the same in both these cases. What we do is we subtract in one direction, then subtract in the other direction, get the square of that, and then get the square root of it. So it's basically just finding the hypotenuse of things in different directions, and then we also find the sigma by doing those. I can't remember. Do we have to do an arctan over that or not? I'll check that out for you. I have a feeling I may have left out an arctan there that should be in there. It might have just not come up in the thing. I'll look for it again anyway, because normally we won't find an angle if we don't do something like that. So I have a feeling I've just left that out of it there. So this is you've done this before with vectors here, where you've got something in that direction and something in this direction here. They're x and y, so they're in opposite directions to each other. And what we want to do is we want to find the magnitude of this, which we get by using the hypotenuse here. So using Pythagoras there, and then we want to find that angle there, and that's basically going to be the arc. Excuse me, arctan of the opposite over the adjacent. Okay, so I have a feeling I've just left out the arctan there, and it should be there. Okay, so that's how we calculate the orientations for each of our gradients at different positions around the image. What we then do is we do an orientation histogram, and this was something that was very much of its time. It turned up in Hogg as well, the histogram of oriented gradients, which is actually named after it. And the idea here is that what we do is we look at all the different gradient directions, and we form a histogram from these orientations of the sample points within the region around the key point. Now remember that we have a key point at a particular position at a particular scale, so therefore we need to look at the gradients at that scale and over those distances. The orientation histogram has 36 bins in it, so that covers the 360 degree range, so we can tell within about 10 degrees what the direction of the gradient is going to be. So if it happens to be that you have one gradient at 55 degrees and you have another one at 57 degrees, then they're both going to get put into the one bin and get added together. Now each sample is added to the histogram after it is weighted by its gradient magnitude, which means that if the one at 55 has a big magnitude and the one at 57 has a small magnitude, they both get added, but one gets added with a greater weighting than the other, so that we find out where the dominant gradient is. So this isn't that each one gets an equal vote. Instead, it's weighted by the actual size of the magnitude. So it's added to the histogram after it is weighted by its gradient magnitude, and it's also weighted by a Gaussian circular window with a sigma of 1.5 times the scale of the key point. So whatever our sigma is at that key point, we're then going to multiply. We're then going to get a Gaussian that's 1.5 times that, and we're going to do weighting over that. So the idea here is that if a particular gradient is a big gradient, then more of it gets added. But if it's further from our key point, it gets less of a weighting. So you could have a situation where a fairly small magnitude that's close to the feature point gets a higher weighting, or get more of that goes into the bin of the histogram than one that's further away that has a larger magnitude, because the two things will compete with each other. So it's that's the mechanism by which they fill up this histogram. So the highest peak, the peaks in the orientation histogram correspond to the dominant directions in the surrounding area of the feature point. The highest peak in the histogram is detected, and then if there's any other local peak that is within 80% of the highest peak, it's also used. So we'll use two of them to create a key point with that orientation. So for locations with multiple peaks of similar magnitude, there will be multiple key points created at the same location and scale, but different orientations. And what this basically means is that we will have two different descriptors for the same feature. because either of them could be important, and it just means that at that particular point in the image there's a whole lot going on. Okay, so generally speaking, on average there's only about 15% of our feature points that are assigned multiple orientations. Most of them are only assigned a single orientation because they have a single most important orientation within the histogram. Remember, there's 36 bins in this, so one of them is bigger than all the rest, and it has to be bigger it has to be bigger by in other words, the second biggest one must be only less than 80% of the biggest one for you to only have one. But about 15% of them have two that are two or three maybe that are quite dominant, and you do separate ones for each one of them. Finally, what you do is you fit a parabola fit to the three histogram values closest to each peak to interpolate the peak position for better accuracy. So the problem here is that you've got a bin, you've got three bins that are covering maybe 30 degrees, and you want to find out, well, okay, was I dead center of that bin, or was I maybe closer to the edge of it? And so what we do is we fit a parabola over the three histogram values, so one on either side, in order to try and find where was the actual maximum. Because we may find that if we have three, let's say I'll use the different type of pen here. So we've got three values in our histogram. Okay, so we might have another one here. Sorry, there. What happens is that when we fit a parabola for it, we may find that it goes something along the lines of that, and that our peak should actually be here. Okay, so that's the idea of doing that. It gives us a bit better accuracy. So the peak is important. It tells us the dominant orientation of the whole feature. So now remember that what we have is we now know where is the feature located in this current image. We know what scale it's at in the current image, and we now know what the dominant orientation is within the current image. So because we know the dominant orientation, we're now later on going to find out a descriptor that is relative to each of those different things. And that means that if in some other image it's at a different location, and it's at a different scale, and it's at a different orientation, that's okay, because everything is done relative to those three things, and we should then still be able to see the same things happening. So along with the scale, location scale, this is the third piece of information that will be used as the anchor that the rest of the feature descriptor will be relative to. So when we compare one descriptor to another descriptor in two images, we don't compare these three values. These three values are only there to tell us where to go and find them within the image. So we can put the descriptors into a database, and then we say, well, here's the places that you find them. You'll find them at this location, this scale, and at this orientation. So the previous operations have assigned an image location, scale, and orientation to each key point. Now what we want to do is we want to use these parameters to do our to make our actual descriptor. So these parameters impose a repeatable local 2D coordinate system in which to describe the local image region, and therefore provide invariance to these parameters. So the next step is to compute a descriptor for the local image region that is highly distinctive, yet is invariant as possible to remaining variations such as change in illumination or a 3D viewpoint. So here's what the descriptor looks like. What we do is we look at the, and I'm wary of saying pixel here because these are not strictly pixels. Because where they are depends on our sigma value, so it depends very much on our scale. So you can think of this, if this was in our high resolution, our top resolution image before we've changed any of the scale, you can think of these as pixels. And we're looking at what is the gradient at each of these different pixels around the place. So what's the gradient at each of these different places around our central point. And of course, there's always the danger then when you talk about a central point, because is that a pixel, is that the center, or is that the center, or is that the center? So in most cases what we're doing is we're doing an interpolation around this. We're going some distance out and figuring out what's our gradient at that point, and so it should be relatively central and circular around that. Okay, so what we do here is we go and we find those gradients, and once again we're going to put those into a histogram, but this histogram is a little bit more coarse than the previous one. Yeah, so I'm going to come to that in 1 second, Vin. So just hold that question for 1 minute, and I'll be showing you that on I think it's actually on the next slide. Okay, so we'll see that at that point. So we'll see exactly what occurs in that situation. So what we do is we go and we find these gradients and we put them into a histogram. So Maurice is asking, is it like changing a pixel-based image to a gradient-based image? No, not exactly, in that all we want to know is we're not actually going to change this into a different image. Admittedly, you can see there that this little section here looks like an image, and we have, as I mentioned earlier, pre-computed all of these. So you can think of that as if we have an actual image at a particular scale with just these gradients. So that's not a bad way to think about it. What we then have to do is, for each section of 4x4, is make up a histogram. And we can see the histogram kind of shown here. And what we have is what we're going to do is we're going to look at the ones, like, let's say, for example, that one's pointed directly up and maybe that one's pointed directly up there. So we're going to add those two together and it's going to come to those ones. We have another one there as well, okay? The other thing as well is, when we're adding into this, is that circle there, and again, I'll be going through all this in the next few slides as well, but that circle there represents a Gaussian. Okay. Now, exactly where we're only shown as a circle, so we can't see the kind of three-dimensionality of it here. But what that's basically saying is that this one here is going to be treated with higher precedence than, let's say, this one here. So it's going to add more to this when it comes to it than that. Now, what we do is we just write these out as so this each block here, we write that out as a particular set. So we write each one of them like this. So we just put their number, so that number maybe goes in there, and then that number goes in there, then that number goes in there, and so on. So we write that out as a descriptor, okay? And we do that for each one of these, okay? Now, we have to get back to, though, how do we end up, how does that not all change with rotation and so on? So, where did it? I had done this earlier and I've obviously gone and deleted it, so I'll redo it here. So how do we deal with rotation then? So let's take our screenshot here. I'll just move it onto here. Vin, I'm not sure I understand your question. Can you run on key descriptor Gaussian? Maybe you might just reword that as I'm drawing here. So just as I'm drawing here, right? If we take this, let's say that this is our feature in one particular image, and this is the scale that it's at, and so on. Okay, and we record all of our Gaussian on a set of key descriptors. We're running the Gaussian here on the gradients. Okay, in order to determine the descriptor. We don't then do it on the descriptor, if that's the question you're asking me. So in other words, to create the descriptor, we do the Gaussian on it first. Hope that's the question you're asking me. Okay, so let's imagine that this same feature turns up in another image, okay? In the other image, what we have is, so let's say, for example, in this first image, our dominant direction was, let's say, that there. Okay, so that's our dominant direction. And then we figure out our gradients, our histogram of our different histograms of gradients there. If we go into another image and we find that, or what we do is we find a feature, and we find that this is its dominant orientation. Okay, there, that should be a little bit more clear. And we find that it's at a smaller, that it's at this scale. Then we do our gradients relative to that scale. Okay, and that means then that the descriptor that this one comes up with will be the exact same as the descriptor that this one comes up with. Okay, So the two will be the exact same. So that's how we deal with the rotation. Earlier on, we determined exactly the rotation that it was at. And it means then that when we come across it later, so in other words, if we come across this again in some other image, sorry, I'll just do a screenshot over there, copy. So once again, it could be much smaller and it could be pointed in a completely different direction. But because all of the gradients are being done at that scale and it's been done relative to that orientation, that means that our descriptor should be the same in each case. Does that make sense to the guys there, particularly that were at Vinya? I think you were asking me about the rotation. Does that make a little bit more sense now as to how we deal with those? Yeah, okay. So that's how we tell the difference. So that's why it's important that we don't mix up those two steps. In the first case, we have a histogram bin with 36 bins, and we find the dominant orientation, and we try and get as good as clear as we can. Remember that we're going to go to another image, and we're just going to happen upon the same thing, and it's going to be at a different orientation, different scale, different location. But when we do up the descriptor, because everything's done relative to those, we should find that the two descriptors match across scales, across locations, and across different orientations. Once we then get each of these different ones here, so once we have these ones here and each one of these, we then just make a histogram out of that. Now I think they done it slightly differently than I did it. I said that I put this top one up there, but of course we should really start with this one here, is the normal way of doing things. As long as, it actually wouldn't really matter as long as we were consistent, okay? But I assume that this is probably what they've done. This is from Selesky's book. So what he's basically said was, okay, when we have this one, this goes in here like that. I assume that this is the next one. I assume he's going in that direction. I'm not absolutely definite. Then that's that one. Then that's the small one. Then we've that one there. Then we've a small one. Then that one there. And that one is roughly the same size. So I think I've gone in the right direction there. So going from 0 around to 2 pi. So we've a much coarser one here. Rather than having 36 bins here, we only have 8 of them, as you can see there. So first, the image gradient magnitudes and orientations are sampled around the key point location using the scale of the key point to select the Gaussian blur for the image. To achieve orientation invariance, the coordinates of the descriptor and the gradient orientations are rotated relative to the key point orientation, which is what I just kind of drew out for you there. So they have to be rotated, otherwise we won't be able to match them up. Okay. So a Gaussian weighting function of sigma equal to half the width of the descriptor window is used to assign a weighting to the magnitude of each sample point. And that's the circle that's shown in the figure there. So bear in mind that that's separate from the Gaussian that got mentioned a few minutes ago, which was, where did I have it? I can't remember where I had it, where I said it was 1.5 times it. Yeah, I think it was here. That's separate to that because that's finding the dominant orientation. We've already found that, we've rotated to it, and now we're doing this descriptor here. And so this Gaussian here is related to half the size, or its standard deviation or sigma value is half the size or half the width of the descriptor window. That's used to assign a weighting to the magnitude of each sample point. And that's the circle, as I said, in the figure. So the important point there is, once again, we need to know the scale in order to determine what's the size of that Gaussian, and also in order to determine the appropriate scale that we should be calculating our gradients at. So this prevents sudden changes in the descriptor with small changes in the position of the window. So you can imagine that if we just move that window slightly, and we which we had a certain amount of coarseness with regard to our orientation, we might be out by a few degrees. And so the problem is that if we move by 1 or 2 degrees there, that could have a significant effect on those, and we mitigate that by the fact that we have that Gaussian window on it there. So it prevents sudden changes in the descriptor with small changes in the position of the window, and to give less emphasis to gradients, obviously, that are far from the center of the descriptor, as these are most affected by misregistration errors. So, in other words, if you haven't perfectly lined the thing up exactly as you should. Okay, so The key point descriptor is shown on the right of that figure, which we went through there. It allows for significant shift in gradient positions by creating orientation histograms over a 4x4 sample region. The figure shows 8 directions for each orientation histogram, with the length of each arrow corresponding to the magnitude of that histogram entry. A gradient sample on the left can shift up to 4 sample positions while still contributing to the same histogram on the right, thereby achieving the objective of allowing larger positional shifts. So just to explain that, what that basically means is that, let's say for example this one here, it could have quite a shift. It could move all the way over to here and it would still get added into the histogram in the same manner as it was. Admittedly, it'll be smoothed a little bit more by the Gaussian and so on, but it has a lot more room to maneuver before it actually falls out of the bin entirely. Now, obviously, ones on the edge here, which are given very little credence, if they move over too, then they fall out of it. But the thing is that it allows us a certain amount of variability here. However, we do still have problems where if that one moved over into there, that there's still a bit of an issue. So he was concerned about that sort of thing, about it falling into other bins, and we talk about that now in a second. So just to say that once again, that a gradient sample on the left can shift up to 4 sample positions while still contributing to the same histogram on the right, thereby achieving the objective of allowing for larger positional shifts. I probably should have put this earlier, but anyway, I put this in. I only added this in this morning before the notes went up. So there's a nice, if you look up SIFT on OpenCV, you'll find a nice bit of code there that will actually give you these really nice visualization of what happens in SIFT. Now the problem is that because SIFT is proprietary and it's patented, the most recent version of OpenCV, it's actually a contributing version of OpenCV, so it's not the CV2 that you probably have installed. You have to install OpenCV contrib. But the latest version of that just tells you that it's patented, so you have to actually uninstall and go back to an earlier version. I had to do quite a bit of searching to get it because I just wanted to show it here. So what these circles show is something about the scale of the feature that it's found. And you can see if we look at this one that what it has found is 2 dominant. So 2 dominant ones, one in that direction and one in this direction. So 2 dominant gradients. So clearly one, each of these was within its 36 bin histogram. 2 of the bins were within 80% of each other. Okay. Now in most cases we don't have that. So if you look at any of this, if you look at this blue one here, for example, we only have 1 dominant direction. This green one here only has 1 dominant direction as well. We have a few on the car here that have 2 dominant directions, and that must be going over that the ridge in the bumper. Don't be fooled by that line there. That is actually part of a very large one that goes all the way around here and round to there, and it seems to have 2 dominant directions as well, which are there and there. Okay, so it's just a nice visualization of those, and that shows the dominant direction, so that if it then finds it in another image, those dominant directions will still be there. So it's going to do a separate descriptor for that one and a separate descriptor for that one, so that it can find either of those when it goes looking for it, and it'll do it at that scale. So the size of the circle shows the scales. So it's important to avoid boundary effects. So this is the issue I mentioned, where it could accidentally slip from one histogram into another. So in which the descriptor abruptly changes as a sample shifts smoothly from being in one histogram to another, or from one orientation to another. Therefore, trilinear interpolation is used to distribute the values of each gradient sample into adjacent histogram bins. So it's not just a simple jump into one from the other. They do a smooth transition from one to the other using interpolation again. So each entry in a bin is multiplied by a value of 1 minus d for each dimension. So bearing in mind that the dimensions can be in X and Y, but you could also be maybe looking at scale, where d is the distance of the sample from the central value of the bin as measured in units of the histogram bin spacing. Okay, so I think in that they're only looking at, I don't think they do that over the scale actually. I think it's only in the X and Y there, because it's a little bit more difficult to do it over the scale. So the descriptor is formed from a vector containing the values of all the orientation histogram entries corresponding to the lengths of the arrows on the right hand side of the figure. Now the figure that we have shows a 2x2 array of orientation histograms, whereas the experiments in the paper show that the best results are achieved with a 4x4 array of histograms with 8 orientation bins in each. So this leads to a 4x4x8, which is a 128 element feature vector for each key point. So what that basically means is that while in the diagram he shows us a 4x4 here, or sorry, a 2x2, what they actually have is a 4x4. So you're going to have is it 4x4? He said. I'll just check it here. Sorry, a 2x2 array, but they use a 4x4. So what that basically means is that we're going to be at the center of a. So you're basically going to have another pile of these. What I'll maybe do is I'll just make another. There, just give me 1 second just to show you what that's going to look like. So we'll. Didn't mean to do that. So they'll have to match up against that there. You'll have a second one. So third there. Not doing this perfectly, obviously, because we can't see over them. And a fourth here. So we're going to have that. And we're then going to do from the center there. We're going to do from the center here. And we'll have a Gaussian that goes across across all of them. So it basically goes around there like that. Okay, so it'll be like that across all of them. Okay, so that's what he's saying. Now the thing is that he's saying that within his results, that was the best that he found, was to do it over that size. And the idea then is that we'd still have each of these splits here, and we would still use 8 bins within our histograms. So overall, that means that there will be 128 element feature vector for each of the key points. No, they're not. No. So all I'm saying is that Vin is asking, are all 4 images the same? They're not. What I'm saying is that we just spread much further than we showed in the original diagram. So we're spreading to a bit further. We're just taking more gradients into account. So what that means is that in terms of each histogram will have 8 bins in it, and we're going to so altogether we will have 128 bins that will cover that entire that, and it'll be in a particular order as well, so they should all match up. So the idea here is that if we have a descriptor that has from 1 to 128 numbers in it, and that happens to match another one that's the same as that, because remember that they're all in the same order and they're all at the same, they're all relative to the orientation. So if we get a match or a very close match between two of these, then we're fairly certain we have it. And what's attached to this is we have location, we have scale, and we have orientation. And attached to this one we also have location, scale, and orientation. So when we find a match between two of these, we can then go and find exactly where it is and what orientation and scale it's at to find it back. So these don't get matched with each other because there's that makes no sense. They're not going to be in the same place. But these two descriptors get matched with each other, and they're invariant to quite a lot of things. So there's a few problems that we still have to deal with. So the feature vector, is modified to reduce the effects of illumination change. So what happens if between two of the images we get an illumination change? Does that change our gradients firstly? So the first vector is normalized. The vector is normalized to unit length. So what that basically means is that when we get our vectors here, okay. Sorry, just switch that off. That's why I have it here. Okay, so let's take this here. this is one of them, and we're going to have another, so we've 8 of those, so 8 into 128 goes in how many times? It's that my brain has stopped working at this stage. 128 divided by 8. 16, yeah, there's 16 of them. Okay, so we're going to have 16 of these in a row, okay, as different numbers. So you can imagine these different numbers going for another 16 of those. And what we do is we normalize it. Now, normalizing can mean a number of different things, and I don't know exactly what it means in this case. It either means that we take our largest one and we set that to a value of 1 and everything else is set relative to that. Or what we do is we add up the total. This is probably the more likely one. We add up the total of all our values and divide every one of our numbers by that value. Okay, to mean that the entire, if we integrate, in other words, if we added up all the values, they would all add up to 1. And we do that with absolutely every descriptor, so that really all that should happen then is that we're dealing with things along the same, roughly along the same values, and we're doing a thing to it. So what that would mean then is that if something was to happen to multiply everything by 2 here, that would make no difference, because once we do our, in other words, if some brightness was to change everything, that would make no difference, because when we bring everything back down to its normalized value, the 2 will still look the same. So that's the first thing. So if the change in image contrast changes each pixel by multiplying it by a constant, this will multiply the gradients by the same constant. So this constant change will be cancelled by the vector normalization. We'll just divide by a larger number. A brightness change in which a constant is added to the image pixel, so this is a different type of brightness change, will not affect the gradient values as they are computed from pixel differences. So just in case I'm sure you're familiar with this from differentiation, but when gradients are all to do with differentiation. So let's say if I have x squared plus x, so I get the derivative of this and I get 2x plus 1. Now, what happens if I was to add a constant to this? So let's say I add the number 2. Well, it makes no effect on my gradient, as you can see. Okay, so because the derivative of 2 would just be 0, so it would be just a plus 0. What happens if I multiply everything by 2? So if I multiply this by 2, so I get 2x squared plus 2x, that would give me 4x plus 2, which is exactly twice what I just had. So it's multiplying by effectively by the same constant. Okay, and that's the two different types of changes that we're taking care of there. One by normalizing, and the other by the fact that if it's just an additive change, it will not affect the gradient. Okay, so therefore the descriptor is invariant to affine changes in illumination. We can have situations where we have a non-linear change in illumination. And this can cause a large change in relative magnitudes of some gradients, but are less likely to affect the gradient orientations. So the orientation is probably not going to change, but we could have significant changes in the magnitudes. Therefore, to reduce the influence of large gradient magnitudes, what we do is we threshold the values in the unit feature vector to each be no larger than 0.2 and then renormalize to unit length. So matching the magnitudes for large gradients is no longer as important. Instead, the distribution of orientations has greater emphasis. So the value of 0.2 is determined experimentally using images containing differing illuminations of the same 3D objects. Now, what that basically means here is that if we go back to our example here, let's say, for example, that this value was very, very large in comparison to the rest. What we would do is we would just set a threshold and say you can't be larger than 0.2. So we're going to ignore everything that's above that. And the idea here is that very large magnitudes are going to cause us trouble. So very large individual magnitudes of gradients will cause us trouble because they could be caused by something like noise, or they could be caused by some illumination problem. So if later on we calculate this feature in some other image at some other point and it's even larger, well, that makes no difference. It can't go above 0.2, so we're just going to cap it at that, and then we do our renormalization. And hopefully then the rest of these relative to that will all be fine, and they'll all be very visible. So it means that you spread out the finding of this, and you don't rely on one particular image gradient. You're relying on the overall distribution of them. Okay, so that's it for tonight, guys. Thank you for maintaining your attention for that long. I know it was a very long lecture tonight, but hopefully you now have a better understanding of SIFT. It is a very important concept, so hopefully you've got a little bit from that. I do really encourage you to read the paper. I know it's 26 pages, and maybe you may prefer to leave it until after your exams or something, but do definitely take a read of it. It's a very good paper, and as I say, it really shows you the whole idea of how you pick your best values, and it shows you maybe how you should be setting up your experiments in order to pick values for and so on for those things. So there's good learning in it, even beyond the synopsis that we have here. Okay, I'll say goodnight to you at that.